Okay, so we're given that g of x equals e to the x sine x, and I want to find g prime. So the first thing I'll notice is that I'm going to need to use the chain rule because this inside part is x sine x. So g prime of x will be e to the x sine x. We're going to leave the inside part alone. The derivative of e to the stuff is just going to be e to that stuff. And here I need to take the derivative of this x sine x. So when I take the derivative of x sine x, I'll need to notice that this x times sine x is a product of two things. So to take the derivative of x times sine x, I need to use the product rule. And so the derivative of x is 1 times sine x, leave the second one alone, plus leave the x alone, and then take the derivative of sine x, which is cosine x. And you can leave it just like that. For the next one, I want to find the second derivative. Okay, so my f of x is negative natural log of cosine x. So to find f prime, I'm going to again have to use the chain rule. So it'll be negative. The derivative of natural log is 1 over. So it'll be 1 over. I'm going to leave the inside function alone, cosine x, times the derivative of cosine x is negative sine x. And so if I simplify that, the negative and negative make that positive. It'll be sine over cosine, which is equivalent to tangent x. And then if I do f double prime, that gives me the derivative of tangent is secant squared. And if you don't remember the derivative of tangent, you can always derive it from using like the quotient rule and sine and cosine, because you know that tangent of x is equal to sine x over cosine x. So as long as you know the derivatives of sine and cosine, you can figure out the derivative of tangent or cotangent or whatever using your other derivative rules. But if you remember that the derivative of tangent is secant squared, you could just go straight to that. So the next one, I'm given some implicitly defined function. And so I want to find dy dx for this function. So your e to the y, the derivative of that with respect to x will be e to the y. And now I want to take the derivative of the inside part, the derivative of the y, which is dy dx. Minus, now I want to take the derivative of x squared y. I'm going to use product rule there. So it'll be 2x times y plus x squared. The derivative of y with respect to x is dy dx equals the derivative of 5 with respect to x is 0. Next, I'm going to distribute that negative sign to both of those, and then I'll also move things around so that I have the things with dy dx on one side and add the things that don't have dy dx onto the other side. So I'll have e to the y dy dx, and then I'll get minus 2xy, which I can add to the other side. And then the minus goes here, so I'll have minus x squared dy dx. And now I can factor out the dy dx and divide by what I have left over. So I'll have 2xy divided by e to the y minus x squared. Next, I want to evaluate the following integrals. So an antiderivative for secant squared is tangent. So I'll have tangent of t minus, here I have a power. So the power of t is going to go up by 1, and then I'll divide by the new power. So I'll have 9 divided by 3, t to the third. And then this is an indefinite integral, so I'll need to have my plus c. For this definite integral, I'm going to see that I'm going to need to use the kind of like the integral version of chain rule, which we call a u substitution. So I'll let u equal x squared, which means du is equal to 2x dx. There are several ways of thinking about this, so I'll just kind of explain it the way I say it to my students. If I were to go ahead and try to do my substitution, I would see definitely that I have an e to the u, and then I have an x dx, which are going to contribute to my du here. But I need to deal with this 2 because I don't have a 2x dx, I just have an x dx. So one way to deal with that 2 is you could think of x dx as du divided by 2, or you could think of it as multiplying by 2 and 1/2 to get that 2 in to come in there. Either way, I'm going to write it this way as the integral. I'll write as 1/2 the integral from 2 to 3 of e to the x squared times 2x dx. So what I did here is I multiplied this 2 in here and this 1/2 outside. So that's just like multiplying by 1 in a fancy way so that I get my du to show up. And now I'm ready to do my substitution. This here is my du. This is e to the u. And then I can change my bounds to be, instead of x values, I can change them to u values. So what is u when x is 3? So I know u is equal to x squared, so u is 3 squared, which is 9. And if x is 2, that means u is 2 squared, which is 4. So it'll be 1/2 the integral from 4 to 9 e to the u du. So an antiderivative of e to the u is just e to the u. And I'm going to evaluate that from 4 to 9. So that'll be 1/2 e to the 9th minus 1/2 e to the 4th. And that's my final answer. The next one, I'm going to apply the fundamental theorem of calculus part 2. So anytime you see this like derivative and integral next to each other, that's going to be the fundamental theorem of calculus part 2. But note that the function that I have there is not just a plain x. So when I apply the fundamental theorem of calculus part 2, I also need to apply the chain rule. And so this is going to end up being cosine of 2 times, I'm going to plug in for theta the x to the 4th, plus 1, and then times, by the chain rule, I need to multiply by the derivative of the x to the 4th, which will be 4x cubed. So this part here is from the chain rule, but I'm going to plug that x to the 4th in for theta, and then by the chain rule, I need to multiply by the derivative of that. Okay, for this one, all right, there's a lot going on here, so let's just take it one thing at a time. The first says the limit as x goes to -2 of f of x. So as I come in from the left and the right to -2, my y values are both approaching 1. So the answer here is 1. The derivative at x equal -7. So -7 is here, so I just need to compute the slope of this line. So it looks like if I go back 1, I go up 1.5. So the slope is -1.5. So if I go forward 1, I go down 1.5. Next, it says the integral from -2 to 2 of f of x dx. So let's see what that is going to be. So I want to compute the area underneath the curve from -2 to 2. So that would be this area and that area. This area is positive and this other area is negative, and it looks like they're exactly the same. So the integral of that, when I add the positive area and negative area, I'm going to get 0. All right, the next one, f prime of -4. So I go here to -4, and I can see that the derivative, the function has slope 0 there, so the derivative of that is 0. The limit as x approaches -6 from the right. So as x approaches -6 from the right, my y value is coming down to 1. This is the definition of derivative evaluated at 8. So this is f prime of 8. And f prime of 8, again, is the slope of this line, which we found already was -1.5. The limit as x approaches 2 from the right of the derivative. Okay. So as x approaches 2 from the right, the slope is getting closer to a positive infinite slope. So the answer here is infinity. Now I'm not looking, the y values are approaching negative infinity, but I'm not asking about the y values, I'm asking about the slope. So if as I approach 2 from the right, my slopes are getting steeper and steeper. They are a positive slope that's approaching positive infinity. I'm looking at the slopes here. Okay, the next one, as x goes to 3, the limit of f as x goes to 3. So as x goes to 3 from the right and left, my y values are both approaching 0. And then this is looks like a Riemann sum kind of thing. And so let's think about what this is. So I like to kind of write out a few just to kind of get a feel for what it's doing. So if k is 1, it'll be f of 1 plus 1 over n times 1 over n, plus if k equals 2, it'll be f of 1 plus 2 over n times 1 over n, plus dot dot dot, plus when I get to the very last one, it'll be f of 1 plus n over n, so that'll be f of 2 times 1 over n. So this looks like I am plugging in x values from 1 to 2. So from 1 to 2, I'm plugging in x values, and then I'm taking the limit of the number of rectangles as the number of rectangles goes to infinity. So it's going to end up being this area here, which is a rectangle. The base is 1 and the height is -1. So the answer here is -1. So it's that area under the curve from 1 to 2. So this is equal to, in other words, this is equal to the integral from 1 to 2 of f of x dx. Next it says, identify all the values of x in the interval where f is continuous but not differentiable. Okay, so if f is continuous but not differentiable, that means I don't pick up my pencil, but I might have some sort of a cusp, right? Now, I'm given the function f here, so I'm looking for where the slope on the right and left don't match up. So at -2, the slope on the right and left are different slopes. So x equal -2 is one of the answers. Another one is at 6. The function is continuous, but the left and right hand slopes are different slopes. So that's another answer. So those are the two.